to see the screen. Okay, so as we discussed, I think we are talking about AI every day in our life, right? So, lot of areas we are using AI, and they are really smart. But as we saw, they are also not invincible. Okay, so they have also some weaknesses, and they have some limitations. Okay, which we observed in our last session. So in this session, what we'll see is basically what is adversarial AI, okay, and how AI is being tricked, okay. So what what is adversarial AI is basically how attackers are trying to create special inputs. Okay, so these are called as adversarial examples. So with these, they are trying to trick the response of the AI. Okay, so that's what we'll try to understand. Okay, here, and these are all our agenda topics to be covered. Okay. So, what is the adversarial threat model, and what are the evasion attacks? What key evasion attack techniques are there, and what are our defenses against these adversarial attacks, and what would be the real world implications, and what is the future of adversarial AI? And we'll also try to have a quick Q&A session at the end. Okay. So as we discussed, I think AI is integrated into many day-to-day things nowadays. Okay, like self-driving cars and medical diagnosis tools and various cybersecurity methodologies. And as we saw, though they are powerful, they are not. They're not infallible, which means that there is still scope for attackers to break through and make some disruptions in the way they are working. Okay, so basically the traditional measures or the traditional ways cannot address these vulnerabilities. Okay, so we'll need something um, more advanced. Okay. So, what is adversarial AI? It is a field that studies how to manipulate the AI systems. So, as we said, these adversarial attacks are designed to deceive the response of the LLM. Okay. So, basically, it will force the LLM to give an incorrect output. Okay. So, how we are forcing the language model to give an incorrect output is by manipulating the input data. Okay. So it is basically we are trying to deceive the LLM with this adversarial attack. So when I say we, not we, but whoever is doing the malware attacks. Okay. So why is this an issue? Because if you see, if there is an automated signaling system on the road, for example, okay, which we might also use very shortly, right? So, if there is a stop sign on the highway, and uh, the image is modified in such a way that it will not be identified as a stop sign, but as a speed limit, for example. Okay. So stop sign usually has a cross line, right? With a red mark, right? So the image is slightly altered. So instead of that line, there is a number, for example, some 40 or something. So definitely everyone will think that it is a speed limit sign, right? So if that is the case, what will happen to the self-driving car? You just try to imagine. So the self-driving car will think that it is a speed limit sign, and it will go as per that speed. Okay, it will not stop. So obviously that will result in an accident, right? And basically, it is not just one accident, but the entire trust goes, right? So, for example, a self-driving car comes on the road, and immediately on the second day, for example, it meets with an accident. No one will trust, right? So they'll think that probably that it is not technically ready to uh, to deal with this situation, and probably we should not be using this anymore. That's how people will perceive it, right? So the trust will be broken. So uh, take the example of a medical diagnosis. Okay, let's take that. And if a patient is diagnosed incorrectly, for example, the imaging is mainly used to detect, say, various kind of abnormalities in the organs, right? So if an image is manipulated, say, for example, so obviously the specialist or the radiologist will think that there is an abnormality in that organ, and he'll suggest some kind of treatment, right? Probably a surgery or probably a medication to correct that anomaly in that in that organ, because the scan report shows that there is an anomaly, right? So which is again loss to the patient, and probably the loss will be much more widespread, not only for the patient, but the entire family will get impacted because of this treatment, because it might be very costly, and probably the misdiagnosis will come to light after a while, and the doctor will lose his trustworthiness, and ultimately even the hospital might pay some penalties. So the impact we can see is much much wider. It is not just a one-off case, is what I am trying to say. Okay, so it will not be very limited to that one person or one case, one particular case. So just one imaging also, if the attackers are able to modify, that will result in so and so a number of effects, right? So that's why we have to be very careful, okay, with this adversarial AI attacks, and we have to protect our LLMs and make them foolproof. Okay, so that's what we'll try to understand going forward. Okay, so so basically in these images, when we talk about image manipulation, what is being done is they are making it as a very clever modification. Okay, so for humans it will still be appearing as a proper thing. Okay, but for AI it will get completely misaligned. Okay, so seeing that image, AI will get confused. So even that stop sign example, as I said earlier, probably if with human eye, we might still think it as a stop sign, because overall, when we look at a distance, from a distance, the color of the symbol and the line, the straight line, all might be similar or same. We might not even notice the difference, and we'll still probably assume it as a stop sign. But the slight modification, the slight change that they do will get AI to confuse. Okay, so how the the disguise in the images is happening. Okay, so such that humans will still probably correctly assess it, but AI will not assess it. Okay, so next, moving on to this type of attacks. Okay, so in the adversarial threat model, there are two types. Okay, so when we talk about the knowledge levels, white box attack is one where the attacker will know everything about the AI. Okay, so how the model is working, what kind of input is being fed, what is the logic it is following, how it is generating the output. Everything is available for the attacker. Okay, in the white box methodology, because probably it is an open source code, for example, open source model, then everything will be available, right? So attacker will have knowledge of everything. So let's look at a black box model where only the inputs are known to us and also the outputs. So in this case, the hacker will only know the queries, okay, or inputs. For example, let's take a cloud AI model, okay, like Google Vision, okay, as an example. So if we are giving some queries to Google Vision, we know by seeing the output, we can understand how it works internally. Okay, so what the hacker will do when in case of a black box attack is he'll send multiple queries to this Google Vision, and he will get the multiple outputs. He'll try to analyze all these inputs and outputs and try to work out a methodology based on which this model is working internally. So the internal logic and everything is trying to be predicted by the attacker. So because what we can say, it's a more realistic scenario, right? Where say not everyone will use an open source model, right? So many companies will use a proprietary model. Okay, so how to attack this proprietary model? I think is by using this black box technique, where the hacker is sending multiple queries and trying to understand the functionality. Okay, so next, moving on, what are the goals of the attacker? Okay, so it can be a targeted goal. Okay, so when we say targeted, the attacker wants to force the model to produce one specific output. Okay, so as we said earlier, in the stop sign example, they want to make it as they want to think that the model they want the model to interpret as a speed limit sign. So this is a targeted attack. Okay, so similarly we have non-targeted attacks also. So in a non-targeted attack, so they will just misclassify the input, but they don't want any specific target class. Okay, so how we can make it, how I can tell with an example. Okay, so they'll feed probably a cat photo. Okay, but they're not bothered whether whether the cat is classified as a cat or dog or a car or something else. Okay, so basically they're not willing to put something specific on the output side. Okay, so they just want the cat to be misclassified, okay, but not as a specific thing, okay. So if they want the cat to be classified specifically as a dog, then it comes as a targeted attack, okay, like our stop sign as a speed limit, okay. So some uh, say for example, a student is writing an exam, okay. So if you want to copy one specific answer, okay, you just want that answer from your friend who is sitting nearby, you want to copy just that answer from that friend, you can say it is a targeted kind of attack, okay. And probably you just want to pass the exam, so it doesn't matter which question your friend shares with you, okay. So you can ask for help with any question, okay, whichever he knows. You just want to pass the exam, for example, okay. So that is kind of a non-targeted, we can say, okay. So like that we have these different types of attacks. And next we have evasion attacks. Okay. So evasion attacks are the attacks that occur at the inference phase. So when we say inference phase, that is a phase when the model has just been trained and deployed. Okay. So the attacker modifies the input just enough to evade the model's detection. So which means that he will just give a slight change in the input. Okay. So that tweak is so small that it will just sneak past the system, okay. So usually these type of attacks happen immediately after the AI is deployed, okay. So for example, if a malware is written in such a way that the instructions are just like normal instructions, if they look very harmless, okay, um, even our antivirus softwares, they will just miss it, right? Because if we go to our open file, save file, close file, that example, if some harmless instructions are written, okay, it is not like it is a harmless instruction, but our instructions are looking like harmless instructions. So we have modified it in such a way that they are just appearing like harmless. Then our antivirus software or our malware software will just miss it, right? So those are what we can say as adversarial changes that are being done right now. Okay. So those are classified as the examples. So maliciously crafted inputs. So what example is being given here is, okay, it's an image of a panda, but there is a slight noise pattern that is added to the image. Okay. So for human eye, it will still be, we can still see it as a panda. But for an image classifier algorithm, it will think that it is a gibbon. Okay. Because of that noise that is being added. Okay. So how these adversarial attacks or these evasion attacks are being created, how they are made. Okay. So all the neural networks, they use gradients, right? So I think we slightly touched upon gradient in our last session also. So gradient is the slight change that we are introducing, okay. So into our LLM's knowledge base. So that's how we can say, right? So by moving that input slightly, the attackers will try to confuse the model. Okay. So that way, wrong predictions are being given by the AI model. So how we can say it as, say you don't want your teacher to detect your handwriting. So what the child might do is slightly change the way he writes on his notebook. Okay. So teacher might be using, as for example, an automated scanner to scan those question answers. So the automated scanner might not detect or recognize the student's name. Okay. But but your friend who knows how you write each letter might still recognize it as your handwriting, because everyone writes each letter in a specific way, right? So that's how the slight change that is being introduced, you can relate like that. Okay. So in the input, how we are introducing a slight change is can be compared to that example. Okay. So what we are trying to do is they're trying to calculate the model's gradient with respect to the input, and then the attackers can find the direction in which the input can be changed so that it will cause the LLM to misclassify. Okay. So going in detail into this, we have a couple of techniques again. So this is the fast gradient sign method. Okay. So this is the concept, one of the earliest and simplest for white box attacks. So it calculates the gradients of the loss function and adds a small change to the input in the direction of the gradient. This maximizes the model's loss. Okay. So this is a popular and simpler technique used in adversarial machine learning to generate these examples, adversarial examples. So the primary goal of this FGSM is to create a slightly perturbed input. Okay. So input can be an image or a text, right? So it appears almost identical to the human eye, but for the machine learning model, it will not be uh, it will not be able to identify it. Okay, so it will misclassify it with very high confidence. Okay, so that's basically because of the slight change that has been introduced. Okay, so with this gradient calculation and with the simple loss function and all that, we have successfully made the language model to misclassify it. Okay, so this is a kind of a white box attacks to say, because how the input is being given, how the gradient loss function is affecting the model behavior, all the attacker is able to understand. He has a full knowledge of the model's architecture, the parameters, and how the loss function is impacting, and how the gradient can be changed. So all this complete knowledge the attacker has in this white box technique. Okay, due to this white box attack, and that's why we are able to classify, or rather modify, the input data. Okay, so that the misclassification is done with great confidence. Okay. Okay, before moving on, I think and neural networks are usually trained using this gradient-based optimization. So FGSM essentially reverses this process to maximize the loss instead of minimizing it. Okay. So this is, we can say it's a quick one-step attack. Okay. Because we are quickly able to modify the data and reverse the output, right? And it is like a one-step attack, very quick and have very high impact. Okay, kind of. Okay, so we can think of a spam email with a very slight tweak of words. Okay, like the example I have given earlier. So obviously our whatever tools we have as on today will miss it because it is a very tiny word tweak, right? So that kind of small tweak will have a very huge impact, right? So that can be considered as an FGSM kind of attack, okay, where the change is very small, it is a quick one, and the impact is huge, okay. So what are the advantages of FGSM is basically the simplicity and the computational efficiency, because FGSM is very straightforward to implement, and computationally also it is very inexpensive, okay, when compared to other models. So other models we will discuss next, okay, we will get to understand why it is better. And in the white box scenarios, this is very effective because we can devise very easily an effective way to fool the model, okay, because the attacker has a full knowledge of the model's internals. So how it is working and all, the attacker has all the knowledge. So that is why he can effectively build an adversarial threat which will fool the model, right? And at the same time, there are also some limitations to this FGSM. Okay, so if see, we thought that we'll keep the gradient as a small, right? So this loss function is there, and we'll add a small perturbation to the input. So the change we said was always to be small, right? But in some cases, we'll have to use little bit larger gradient or larger change also in the input, okay, because not always we'll be able to get the model to give a false output with a very small change, right? So sometimes we have to give a little bit larger variation also in terms of input. So in these cases, what happens is it will become noticeable. Okay. So if the input is changed a little bit more, change we have introduced in the input, then definitely there is high probability of getting this intercepted, right? So that we can say as one of the limitation. And and also, if our model is already trained for robustness, right, then it might be less effective. Okay, so basically, we'll need more advanced models in that case. Okay, so that way we'll look at the next projected gradient descent technique. So here, the concept is more iterative in nature. Okay, so since this is kind of an iterative adversarial attack method, so where inputs are designed to cause incorrect predictions. Uh, so basically, what we are trying to address here is in FGSM we had some limitations, right, with respect to the gradients and all. So that we are trying to address here by having some random points as a start. Okay, so in the input data, it is not like always we go with a fixed start point, for example, right? So in this PGD technique, we choose a random point. Okay, so in that random point, we just introduce this small change in the input. So in in our earlier methods, we just did this from the start of the input. Okay, so that is being addressed here, and we just selecting any random point in the input where this change is being introduced. Okay, so in this iterative approach, the gradient is calculated based on the loss function with respect to the input. Okay, and it then takes a small step in the direction that maximizes this loss. So basically, step by step, we are trying to make the progress. Okay, so we are aiming to increase the misclassification probability by making a small step in the direction that maximizes the loss. Okay, so basically, after each step, the the modified input is projected back into this LLM feed. Okay, and this projection ensures that the adversarial example remains close to the original input. Okay, so basically we are making a small change, but again we are trying to make it again into a constrained set. Okay, so that's how we are again trying to adhere to this. Okay, so this kind of we are trying to do this in multiple steps. So these steps are repeated for multiple iterations, and gradually we are trying to introduce this change in the input data, and then finally trying to achieve this misclassification by the LLM. Okay, so actually, I'm also not very satisfied with my explanation, but I think I hope at least you try to understand at a high level what how we are doing this the projected gradient descent with a repetitive kind of perturbations in the input data. Okay, so we are trying to have a data boundary kind of. Okay, and within the data boundary, we are trying to change the data. Okay, so this is considered as a very highly effective and kind of benchmark system for defenses. Okay, and next, moving on, we have a few more transferability. Okay, so basically this is like some adversarial examples which we have created for one model. Okay, and those can be used to fool another different model also. Okay, so basically how we are able to achieve this is because all the deep learning architectures are built on common fundamental principles, right? So that's how these attacks are becoming transferable. Okay, so yeah, so I just found an interesting example for this PGD, okay, which I missed. So it is like, see, for example, in this FGSM, you are just making one disguise, for example. You are dressing yourself up as a Swamiji, for example. Okay, so it is like a one-time thing. You just did it, and everyone believed that you are a Swamiji, and no one recognized you, basically. Okay, that is kind of an FGSM. And in this PGD, it is like you just made one small quick disguise, okay, or one small disguise initially. Then you keep on making some more little bit more additions, little bit changes, and basically finally you arrive at one mask where it's perfect. Okay, no one recognizes you as the original person, and everyone thinks you are a real Swamiji. Okay, so I think that kind of explains it. Okay, and next we move on to this query based attacks. So by repeatedly giving queries to the black box model, and analyzing the outputs, we are trying to understand the internal workings of the model. Okay. So basically, when we say black box, we don't know how the model works, right? So in white box, everything is clear. We know how the model works. Everyone knows because it is an open source code. But in black box, we don't know how the model works. So what the adversarial attacker does is he will give multiple inputs. Okay, multiple questions, and once the LLM provides all the outputs, he'll try to match these outputs, and then he will come up with an understanding of how the model is internally working. Okay. After all this analysis, the adversarial attacker will be able to fully explain the model's working methodology. Okay. So some techniques are also used like this ZOO to get this approach. Okay. So for this query based attacks, you can think like how the attacker keeps probing the model. Okay, so with the different set of questions, they'll try to probe the model and try to understand. Okay, so you can imagine like a thief coming to your house, and he'll try to open each and every door and window. Okay, he'll try to find which window is open. He'll keep rattling against the doors, and finally, if he finds one window is little bit weak, he'll push it and he'll open and come in. Okay, so like that. So similar to that, these query based attacks are planned. Okay, to identify the soft parts. Okay. Next, we have few more other types of attacks. Okay, so this is data poisoning. So data poisoning is a type of adversarial attack where the training data is again intentionally altered, right? So where models are trained on, normally they are trained on massive data sets, right? So particularly if data poisoning is done, almost all models are vulnerable, right? So basically at the learning stage itself, the model is being trained to learn incorrectly. Okay. So this will lead to a biased or inaccurate prediction. Okay. So obviously, if we are training it with wrong data, it will obviously give wrong outcomes only, right? So basically what the attacker is doing here is he is trying to train the model incorrectly, and trying to get the model to behave in a way that benefits the attacker. Okay, so that learning process itself, they are trying to impact. Okay, so this obviously data poisoning will undermine the trust. Okay, because people will think that AI systems are not unreliable and unpredictable, basically, because I think we have all, we saw some news also recently, right, where uh, the top AI chatbots are giving incorrect responses. So for some very silly, relevant questions, but still it is highlighted throughout the world, right? So that's how, like, even a way, it might give 100 correct answers, but one wrong answer will get a lot of attention, right? So that's how the trust is broken. And in safety critical applications, it can have a severe consequence, right? So, and this data poisoning attacks are very, very challenging to detect, because the poison data will always appear as a legitimate data to us. Okay. So if we look at that, we'll not be able to say that it is a poison data. And what we can do as a countermeasure to this is we'll have to have more rigorous validation and verification of the training data. Okay. So techniques like anomaly detection and identifying the outliers and unusual patterns in the training data. So those kind of anomaly detections we have to incorporate. Okay. And also we have to do regular auditing and monitoring of model behavior, which can help detect anomalies and then avoid these potential data poisoning attacks. Okay, and we'll have to build robust training techniques. So our training algorithms have to be robust and they should be less susceptible to data poisoning attacks. And I think this is still, we should be much more, I think, actively researching in this space because obviously, if the data training data is corrupted, we can say the entire our LLM our model itself is corrupted, right? So I think there was a recent Microsoft's this chatbot. Also, I think with someone fed the wrong training data to it, and within 24 hours, it has turned racist. Okay, so that's how the impact of this data poisoning is. Okay. And next we have this model extraction, which is also like stealing. Okay. So this is like the attacker queries a black box model and with he'll try to construct a copy of that. Okay. So basically, what we are trying to say here is in a black box setting, the attacker will access the target model through its input output and then obviously observe the outputs and try to analyze how the model is performing, right? So based on this input output queries, he'll try to simulate all this behavior on another model which he has built. So that is called as a surrogate model. And these inputs and output pairs that he has collected, he'll use it to train his surrogate model. Okay. So that will try to replicate the behavior of the first model. Okay. So this way, uh, he'll try to achieve similar prediction accuracy. Okay, on these tasks, and he'll ultimately be able to create, or his aim is to create a model with a similar behavior. Okay, so basically once he is able to create a model that behaves identically to the model, then basically the model can be attacked, right? Because he can build the strategies on how to attack also, right? So this is like preparing a surrogate model and then uh, train or using it to uh, break the defense mechanism of the original model. Okay, so that's what is being done. Okay, so and this is also kind of a threat to the intellectual property, right? Because uh, the original model owners will have the IPR rights, right? But it is actually this adversarial attacker is unauthorized, it is resulting in an unauthorized replication, right? So he's without uh, any authorization, he is using all that or replicating the functionality. Okay, so basically this is like a multiple kind of impact. Okay, so one is a IPR threat, and the next is the defense mechanism is also broken. Okay. So how we can avoid this is basically by the model's parameters and architecture has to be encrypted. Okay, so if the original model used this encryption or obfuscation techniques, this situation could have been avoided. Okay, so if that was done, probably this surrogate model building and all this exercise could not be successful, right? So what we have to do is input diversification. So using various techniques, the model's behavior should be unpredictable to the attackers. Okay, so behavior should not be predictable, because since it is predictable, that is the reason they were able to replicate it, build a surrogate and all that, right? So if we can make it as unpredictable to the attackers, all this can be avoided. Okay. And next, one more precaution that can be taken is watermarking. Watermarking is like embedding a unique signature or watermark into the model's predictions. So if there is any unauthorized use, that can be detected. Okay. So if an input is fed by an adversarial attacker, that will not have any watermarking, right? So that's how that can be recognized. Okay. And also the hardware can be secured. Okay. So using some secure enclaves or trusted execution environments, so the model can be protected, okay, from unauthorized access. And usually what the attacker does is, until he tries to create, when he's trying to create the surrogate model, he tries repeatedly. Okay, so if we have any kind of mechanism to identify these kind of repeated attacks, then also we can prevent it. Okay, so multiple times, if some access requests are coming, things like that have to be monitored. Okay, so you can think of, say for example, we have this Paytm API app, right? So we can try to uh, build it by testing it multiple times, and we can um, we can try to build our own app like that. So something like that we can relate to. Okay, and there are some more different types of attacks also. Okay, so basically, sorry, I forgot to move the slide, but these were the proactive defenses we were talking about. Okay. So I think this inference attacks also we need to cover. Okay. So one slide I moved quickly, I think. So coming to inference attacks, these attacks aim to infer private or sensitive information from the model's output. Okay. So how this will work is basically uh, they'll and attacker will analyze the publicly available information and indirectly deduce sensitive information that is directly not accessible. Okay, so how this is done, I think we can try to understand. Basically, an attacker trains a machine learning model on a data set similar to the target model's training data. Okay. And by querying the attacker's model, they can infer whether a specific was used to train the target model. Okay. So see, this is like giving a specific query and then trying to see whether this data is part of that query. Okay. So for example, a hospital is training a model to predict patient outcomes. Okay. And attacker could use a similar model to determine if a particular patient's data was part of that hospital's training data or not. So this way, potentially, they will be able to get sensitive health information of that particular patient. Okay. So like that, various kinds of membership information or any kind of inference attacks, we can say. Okay. So they use techniques like correlations or patterns or any kind of subtle cues to uncover this knowledge. Okay. So this is not directly available, but indirectly by using some techniques, the attackers are trying to figure out or infer this data. Okay. For example, you can think of some smart meters. Okay. So these smart meters track the energy consumption patterns. Okay. So if we analyze this data, an attacker can infer information about a user's daily activities. Okay. So like when they are home, when they are using appliances, or even if they are using certain type of devices. Okay. So if we are using that smart monitor, for example, an attacker could monitor our smart meter and determine whether a household is occupied or unoccupied. Okay. And making it a target for some kind of burglary, right? So uh, that's how we can relate this. Okay. And and also an attacker can use sensors on a device to detect subtle movements or vibrations caused by typing. So this information can be used to infer what keys are being typed, right? So I think we saw in some movies also how the passwords are getting revealed with this technique, right? So based on what keys are being pressed, the password information is getting predicted. Okay, so so an attacker can use a microphone to listen to the keystrokes on a keyboard and or use a nearby device to detect vibrations from the keystrokes on a touch screen and determine what keys have been pressed. Okay. So similarly, an attacker can analyze a user's public posts, likes, and connections on social media to infer information about their personal life, relationships, location, or even their political views. See, by analyzing all these users can predict their social media activity, right? So also they can try to gather information on what are their political affiliations and all. Okay, by viewing their posts on social media. So these are the various kinds of techniques that are used to infer information. Okay, and what are the defenses that we can build against these adversarial attacks? So there are proactive defenses. Okay, so how to do this is train our model with normal data and also adversarial data. Okay, so basically we'll give some false data also. Okay, so that's how we are building a stronger model. Okay, and then we'll build some reactive defenses also. Okay, so these reactive defenses, we can say, like you adding some random noise or filters. So this will cancel out the malicious noise. Okay, so by adding random noises, we are trying to suppress the malicious noise. Okay, so like this, we can try to build a lot of defenses, but if we put lot of defenses also, then again our model performance is getting impacted, right? So basically, we try to build so many defenses that our model becomes slower. Okay, so even on legitimate inputs, it will try to validate many things, and finally the output will be much slower. Okay, so we should be careful and not put too many defenses, so that the model performance is not impacted. Okay, so see, it's like we have an antivirus patch coming in our laptops every day, right? So every day, whenever the antivirus patch, none of us hesitates to update it, because that is very much required, right? Because every day we are trying to patch one hole or one area where the hackers will look for an opportunity to come and uh, put the malicious content into our systems. So every time the antivirus is again trying to patch something, and the hackers on the other side are looking to find another loopholes. Okay, so it is kind of an everyday thing, everyday game. Okay, so let's see some real world implications. So adversarial attacks on a car's computer vision system could lead to accidents, and stickers on stop signs, like we said earlier, the stop sign stickers can uh, cause confusion, and they can think it as a speed limit and go right. And modified emails, as we said, slightly modified email, which looks a, a normal one. Our antivirus cannot detect it. Okay, and printed patterns on a shirt can hide our identity. Okay, so with a unique pattern, there are some studies that with a unique pattern, if there are people wearing a similar T-shirt, probably their facial recognition also will be system will not be able to classify it properly. Okay, so similarly, the medical diagnosis. So if an image is modified, so a wrong diagnosis obviously will be the impact, right? As we discussed earlier. So it can be a very small pixel change in a scan, okay? But probably the doctor will identify it as a probably a cancer or something, okay? So which will have a very big impact. So considering all this, what is the future? Okay. So the focus is simply shifting from fooling to more complex attacks, okay, like data poisoning. Okay, so I think that is a bigger threat, right? Poisoning the data, it's by and the model itself will be trained incorrectly, right? So So what we have to focus is on this poisoning, stealing, and these privacy attacks. Okay. So government is also trying to step in, and they are trying to develop for some standards for security and robustness of these AI systems. And probably we might have at some day some guaranteed mathematically guaranteed systems which will certainly restrict these attacks. Okay. Okay, so I think with that almost we are at the end, and we can say that adversarial AI is a major threat to AI security and trustworthiness. And adversarial examples to fool are a core concern. Okay, and we also discussed these key attack techniques, FGSM, PGD, and also some defenses in this adversarial training. And what are the broader implications of these AI systems? Okay. But we also have to understand the risks are very real, because we might think that we are far off and we are not susceptible to these risks at right now. But that's not the case, as you could see from the examples. So what we have to see is make our systems as much robust or as possible from our side. Okay. So I think we should try to make it like that. And probably we'll always be more inclined to keep playing the defensive approach. Okay. Because we need to protect the systems also, right? That's our priority. So we have to see. Okay. So whether we'll remain unhackable or whether we'll be always playing these defense mechanisms. Okay. So I think we came to the end. So though we did consume a little bit more time in the first session, I think we are able to cover it and go pretty quickly in the next one, and overall able to complete on time, I guess. Right. So we can take any questions from anyone. Maybe for a quick 5-10 minutes.
Yeah, dear participants, if you have any queries, you can ask. Yeah, thank you, madam. Thank you, madam.
Yeah, Venkatramulu.
Yeah, you given a wonderful inputs on deep learning for malware detection and classification in the first session. And in the second session, you given a inputs on adversarial AI and model evasion attacks. Yeah, thank you, madam, for your valuable time spare with us in the FDP. So thank you very much.